Fibonacci numbers were created, well, sort of created by a man by the name of Leonard Pisa. He's also known as the brother of Nachi or Fibonacci, um, and he's been around for a while. You actually, if you've ever read the Da Vinci Code, which is a book that was out and a movie that was out recently, Fibonacci numbers showed up in that discussion in that movie. So Fibonacci numbers have been around for a while. They were a way to actually introduce the Arabic number system to Europe that was using the Roman numerals. So the way that they were doing that, and what the Fibonacci numbers deal with, and it involves the golden, it actually relates to the golden ratio, which the ancient Greeks knew about. So the Fibonacci sequence, it's called what a sequence is kind of given to us. We've seen sequences already with linear sequences and exponential sequences back with other things. But this is actually a sequence that's known as a recursive definition. And what that means is that I get the next term from the previous term. With the Fibonacci number, you actually need the first two terms. So you need to start with a 1 and then a 1. And if you add 1 plus 1, you get 2. And if you add 1 plus 2, you get 3. If you add 2 plus 3, you get 5. If you add 3 plus 5, you get 8. If you add 5 plus 8, you get 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. 55 plus 89 is 144, and so forth. You can just keep doing this for a while. This is the first Fibonacci number, so F1, F2, F3, F4, F5, 6, F7, F8, and so forth. 144 is F12. So it just says what number you are in the sequence. We use an F for Fibonacci. So you can use any letter you want, but we use F because of Fibonacci. And so what you can actually think of it as the recursive definition is that f of n, the nth term in the sequence, which is just some arbitrary term that you want to find, is the previous term plus the term before that. So again, the 9th term would be the 8th term plus the 7th term. So 13 plus 21 is 34. So if we want to find f sub 9, you need to have f sub 8 and f sub 7. Because you have to know the first two terms, you have to be given f1 and f2, we do say that n has to be greater than or equal to 3. So if I want to find the 13th term, that means I need the 12th term, because 13 minus 1 is 12, and the 11th term, because 13 minus 2 is 11. So I need the 12th term plus the 11th term. So I need the 89th, which is the 11th term, and 144, which is the 12th term. If I add those together, I get that the 13th term is 233. And you can do this forever. You can keep creating all the Fibonacci numbers as far as you want to go. Of course, if you want the, let's say the 39th and 40th Fibonacci numbers, you really don't want to have to add up all those all the way up. We've gotten to the 13th number here, but now we'd have to have the 14th, 15th, 16th, and so forth, all the way up to the 38th number to get the 39th number, and then the 40th. So there has to be a quicker way to do it. And there is a term called Bennett's formula. It is we're going to do what we call the simplified version. There's a more involved version, but this is the simplified version. And it actually is an explicit description of the Fibonacci sequence, which means you actually find the value you want. So the nth term of this, using this formula, you can actually calculate it straight out, is 1 plus the square root of 5 over 2 to the nth divided by the square root of 5. And then you round it to the nearest integer. So these symbols here, these kind of brackets with an extra line, means round to the nearest integer. So if I want the 39th Fibonacci sequence, then or 39th term, we already found it, but we can do it, well, no, we haven't found it. So we can find it this way. 39th would go here, that's your n. 1 plus the square root of 5 divided by 2 over the square root of 5. So in your calculator, you would need to do parenthesis 1 plus the square root of 5. Make sure you close that parenthesis and then close this one. Divide that number by 2. Close this parenthesis. Remember you had to open this one originally. Raise it to the 39th power and then divide that by the square root of 5. And you get that it's 63,245,986. And then you can do the same, and that would round it. So you would have gotten some decimal number, and you would have to then round it to the nearest integer. And the same thing with this one, 1 plus the square root of 5 over 2. Again, remember, open this parenthesis, 1 plus the square root of 5, close those parentheses, close this parenthesis, divide, actually, I'm sorry, close this one, divide that by 2, close this parenthesis, raise it to the 40th power, and then divide by the square root of 5, and then round it to the nearest integer. So if I want to now find the 41st Fibonacci term, I could go through and use Banach's theorem again, but I already have the 40th and 39th, so I can just add these two together, and I'll get the 41st. If I want to find the 38th term, the 38th is right before the 39th and the 40th. So the way we found the 40th was to add the 39th and 38th. So if I have the 40th and the 39th, I can just subtract them to get the 38th. So you can kind of play around with this a little bit to find these different terms. Again, if you want the 90th term, you want to use this formula. The golden ratio is very much tied to this. It turns out it's kind of interesting. The ancient Greeks actually knew about the golden ratio a long time ago, well before Fibonacci. And they were looking at the idea of taking some length and adding something to it such that they could then get, basically think of it as folding it and getting a golden ratio. So they wanted to cut the length of two pieces such that x and plus 1 gives you this golden ratio, this rectangle. Sorry. So you can have x over x plus 1 equals 1 over x. So you want this ratio, the whole thing, to be similar to this, the original thing. It's kind of what you're looking at. And so you get this ratio of x over x plus 1 equals 1 over x. So think of it as being related to this rectangle here. This length here, this one here is related to that. So you've got your x to the x plus 1, that's your first ratio, is equal to 1 over x, that's your second one. X plus 1 is longer than 1, or longer than x, and we're assuming that x is longer than 1 here. And that gives you x squared equals x plus 1 if you cross multiplied. And then you get this nice little x squared minus x minus 1 equals 0. And we need to now solve this. Well, the ancient Greeks didn't know how to solve this, but we do now. We can use the quadratic formula to solve this. They actually were able to come up with a number for it. It's weird, you won't think of it as a number, but I'll show you what it is in a minute. And what you do is you take, remember the quadratic formula is x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to take our b value, which is this negative 1. We're going to take our a value, which is 1, and we're going to take our c value, which is negative 1. So if I put b, negative 1 in here, put a of 1 and c of negative 1 in here, I'll get negative 1 squared, which is 1, plus 4 times, minus 4 times 1 times negative 1, which is plus 4. So 1 plus 4 is 5, and negative 1 is 1, all over 2. So I get 1 plus the square root plus or minus the square root of 5 over 2. So that's actually 1 plus the square root of 5 over 2, and x is equal to 1 minus the square root of 5 over 2 is the other ratio. I think I've seen that 1 plus the square root of 5 over 2 somewhere before. And look, it's in Banach's theorem formula for finding the Fibonacci numbers. So that 1 plus the square root of 5 over 2 is actually what we call the golden ratio. And the ancient Greeks knew about this golden ratio. They didn't know what the value was of it, but they were able to define it as something. So they knew there was this golden ratio that would relate these things together. And so they came up with a number for it, and they just used their Greek letter phi, or phi. So the golden ratio is this phi letter, and it's actually 1 plus the square root of 5 over 2, which we now know is 1.618. Repeating, this is not actually what it's equal to. It's approximately this. It is, again, another irrational number like pi and e that never ends. In case you don't remember how to solve for a quadratic equation, here's just another example. Again, you're going to take your b, which is negative 5, put negative 5 in everywhere you see a b, take your minus 4 times your a, which is 3, times your c, which is negative 7. Plug those numbers in. Negative 5 squared minus 4 times 3 times negative 7 is 109. And then you're going to have 5 plus or minus the square root of 109 over 6. This again is an irrational number, but you can reduce it a little bit if you want to. So we can reduce a radical. So like 24 is 4 times 6, and the square root of 4 is 2. So you can in fact reduce a little bit by pulling out your perfect squares. 108 is 4 times 27, so the square root of 4 is 2, so 2 times the square root of 27. 27 is 9 times 3, so then you get square root of 9 is 3, so 2 times 3, which is 6. Which actually told me that 36 divided into 108, 36 divided into 108 3 times, and the square root of 36 is in fact 6. So we could have done it that way too. You don't need to reduce the radicals, in my opinion. They're fine this way. In fact, this one doesn't reduce because 109 is not a number that will have a perfect square in it. You're only going to look for perfect squares. So now what the ancient Greeks also decided, and what Fibonacci actually found, is if you look at the ratio of consecutive Fibonacci numbers. So in other words, if I take 1 divided by 1, I get 1. If I take 2 divided by 1, I get 2. 3 divided by 2, I get 1.5. 5 divided by 3, I get 1.66, and so forth. Notice 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. So notice all of a sudden, all of these numbers have a 1.6. 1.6 something, 1.6, 1.6 something. The next one is 21 divided by 13. That's 1.615. The next one, 34 divided by 21, is 1.619. The next one gives me 1.6176. So notice all of a sudden I'm getting 1.61 in all of these. And so then 89 divided by 55 is 1.6182. So again, I'm getting 1.61 something. And if I keep going, I actually get close to this 1.618, which is the golden ratio. So it actually gets closer and closer and closer to 5. And we can do this kind of thing as a limit. You're actually looking, and limits are just where numbers will head as they get bigger, as you keep going on, let x get bigger and bigger and bigger. So if you think about plotting this, we can actually think of these numbers, plot them along an axis, along the x-axis, where the not the x-axis, but along the x values here. So as x is getting bigger, as we're getting farther and farther along the Fibonacci, we're actually looking at the n values here as our x. And as we get longer, farther and longer, they get closer and closer and closer to this phi line. So that tells us the limit of fn over fn minus 1 is phi. This gets us into the last topic of golden rectangles. Golden rectangles are what the ancient Greeks worked a lot with. A golden rectangle is anyone that has the length over the width equal to phi. So they actually knew about the golden rectangles and tried to draw a lot of their architecture using the golden rectangles. So if I want to find the width of a golden rectangle, if the length is 10 feet, so if I know the length is 10 feet, I can find the width. The length of a width, since it's a golden rectangle, is approximately 1.618. I want to find the width. So I've got 10 over the width equals 1.618. Multiply both sides by width to get rid of the fraction. So 10 is equal to 1.618 width, and then divide both sides by 1.618. That gives me a width of approximately 6.18 feet. And the reason I say approximately is because the golden ratio is actually an irrational number that never ever ends. And so it'll keep going. This is just an approximation, but we're pretty close to what the value would be.